Till now, whatever faults we have discussed, those were symmetrical faults. Okay. So symmetrical faults, what will happen? All the three lines will be short circuited with the ground. So there will be no imbalance in the system, right, in the three-phase system. So symmetrical fault, no imbalance in phases. Okay. But what will happen in unsymmetrical faults? There is going to be some imbalance that is being introduced, right? So that is why in order to do the fault analysis for unsymmetrical faults, we cannot make use of the per phase equivalent circuit, right? For symmetrical faults, we have used the per phase equivalent circuits. Because each of the phase is same, we will take just one single phase, we will analyze the fault current, and for the three phases what will be the fault current, right? But non-symmetrical faults, that is not possible. Okay. So what we are going to do here is we are going to use something called as the symmetrical components. So we will first discuss what is this symmetrical components, and once we get an understanding of the symmetrical components, then we can easily do the fault analysis for unsymmetrical faults. Okay. Here you consider an n-phase system, n-phase unbalanced system. So now this n-phase unbalanced system, it can be resolved into n number of balanced systems. Okay, and these n number of balanced systems, these are called as the symmetrical components. Since we are interested in three-phase systems, right, here n will be is equal to 3 for our interest, right. So a three-phase unbalanced system can be resolved into 3 number of balanced systems. So now we will see what are the symmetrical components for this unbalanced three-phase system. Okay. So consider an unbalanced three-phase system. Okay. And let the voltages of the three phases we will take as VA, VB and VC, and the phase sequence is ABC. ABC phase sequence. Now here the first symmetrical component is called as the positive sequence component. Here there is going to be three phases which are balanced, right. So those three phases we are going to write as VA1, VB1 and VC1. Okay. And these are going to be related like this. See, because they are balanced, what will happen? They are going to have equal magnitude. So VA1 mod VA1 is equal to mod VB1 is equal to mod VC1. Okay. And they are going to have 120 degrees phase displacement with respect to each other. These two are anyways given because these are the conditions for a balanced system. Okay. So positive sequence, we say it is a positive sequence because the phase sequence of these three is going to be in same as the original sequence, which is ABC. Okay. ABC phase sequence. This means that VB1, this will be lagging the A phase by 120 degrees, and VC1, this is going to be leading the phase A by plus 120 degrees, or you can say lagging VB1 by 120 degrees, both are same thing. Okay. So this is the relation. Next, second one is the negative sequence component. So this we are going to take the subscript 2, VA2, VB2 and VC2. Okay. So here also the first two conditions will be same, equal magnitude and they will be 120 degrees phase displacement with respect to each other. Now the phase sequence is going to be opposite to that of the original system. So you can take this as ACB phase sequence. Okay. So what will be the relations now? VB2 will not be lagging, but it will be leading the phase A by 120 degrees, and VC2 is going to be lagging VA2 by minus 120 degrees. Okay. Next, last and final, three-phase system. So we are going to have three symmetrical components, right? So positive sequence is done, negative sequence is done. Next is going to be zero sequence component. Okay. So these are represented as VA0, VB0 and VC0. Okay. Now here all of them they are equal in magnitude. There is no difference. Okay. VA0 is equal to VB0 is equal to VC0. But the phase, there is not going to be any phase displacement. They are all going to be in phase with each other. Okay. In phase with each other. That means angle VA0 is equal to angle VB0 is equal to angle VC0. So these are the three symmetrical components. Now the big question is how these are related to our original three-phase unbalanced system having these voltages. Okay. So we will see what is that relation. Each of the phases, they will be equal to their equal to the phasor sum of their sequence components. That means VA will be equal to 0 component of phase A plus the positive sequence component of phase A plus similarly negative sequence component of phase A. Okay. So this is VA. Similarly, VB is equal to VB0 plus VB1 plus VB2 and VC is VC0 plus VC1 plus VC2. Now what we will do is we will try to get a matrix representation of these unbalanced phasors in terms of their symmetrical components. Okay. Once we get the matrix form, it will be easier to utilize while we are doing the fault analysis. Okay. So anyways, this first equation we will leave as it is. VB, what we will do, we will express VB0, VB1 and VB2 in terms of their respective phase A components. So what is VB0 in terms of VA0? This is the zero sequence component. Their phases are equal as well as magnitudes. So VB0 is simply VA0 plus. Now VB1 in terms of VA1. Okay. So this is going to lag the phase A by 120 degrees, right? So what VB1 is equal to VA1 minus 120 degrees, right? So here we will be making use of a parameter called alpha. It is also often written as small letter a. Okay. So you can use anything, alpha or small a. This we take as 1 angle 120 degrees. Okay. So if you square this alpha square or a square, you are going to get 1 angle 240 degrees, or the same thing in negative phase it is minus 120 degrees. Okay. So if you substitute this here, what will you get? VB1 is equal to alpha square VA1. So here alpha square VA1. Now VB2, this is the negative sequence component. So it is going to lead, B phase is going to lead the A phase by 120 degrees. So that is alpha VA2. Okay. Now similarly VC, you are going to write VC0 will be equal to VA0. VC1 will be alpha times VA1 plus alpha square times VA2. So we expressed each of these unbalanced phases in terms of their symmetrical components in terms of the same phase, right? So this is zero sequence component of phase A, positive sequence of phase A, negative sequence of phase A. Similarly here you have A0, A1, A2. right? VC also in terms of A0, A1, A2. Okay. So now we will take this in matrix form. On one side we are going to have VA, VB and VC, right? These are the actual voltages that we are concerned with. Okay. Now here we will see later what this matrix is. Here what we are going to get, VA0, VA1, VA2. Okay. Now you can write what is VA in terms of VA1, VA0, VA1, VA2. It is simply the sum of these, right? So here it is going to be 1, 1 and 1. What about VB? VB is VA0 into 1, alpha square into VA1, alpha into VA2. So here you are going to get 1 alpha square and alpha, right? So 1 alpha square alpha. Similarly here you are going to get 1 alpha alpha square. So this is how you are going to get the matrix representation. This matrix we will take as matrix A, okay, and this matrix we will take as VP. This is the original phasors, and this we will take as VS. So this is the symmetrical component phasors. So this equation is going to be VP is equal to A into Vs. This is the matrix representation that we are looking for. Okay. If it is, this is in terms of voltages, right? Unbalanced voltages we took. Similarly, you can take currents, right? Similarly, for currents, this is going to be IP is equal to A into IS. Okay. So this matrix A is going to be same, but instead of voltages there is going to be currents. That's all. Okay, no other difference. So you can write here this IP is IA, IB and IC, and this IS is IA0, IA1, IA2. Here let me tell you one point which might cause a confusion, because in different books it is written in different ways. Okay. So what we took here, we took the original phasors VA, VB and VC, and what we did, we expressed this in terms of, first we are writing the zero sequence component, remember. Next we are writing the positive sequence, and next finally we are writing the negative sequence, right? And here the A matrix, then it is going to be what? 1, 1 and 1. In the second row it is going to be 1 alpha square and alpha, and finally 1 alpha and alpha square. So remember here the first component that you have is the zero sequence component, and then you have positive and negative sequence. Okay. Now what if you are writing VA, VB and VC will be as it is, but this you are first expressing the positive sequence component, that is VA1, right? And next you have VA2. Next finally you have zero sequence component. Okay. So you can see the first one here is the positive sequence, here this is negative sequence, and this is the zero sequence. In this case what will be the matrix? A matrix, right? This is A. Now here first row it is going to be same, because VA is the sum of these three. So here you are going to write 1, 1 and 1. But VB, this is equal to VA0 plus alpha square VA1 plus alpha VA2, right? So first element here, this is going to be alpha square, and next you get alpha, and next you are going to get 1. Okay. And VC, first you have the positive sequence component, so you are going to have alpha, and next you have alpha square, and next you have 1. Now here this is the A matrix. You can see that these two are different. Okay. So be careful, whenever this equation is given, first verify what is the order of the elements here. Okay. In these lectures we are going to use this notation, the first notation. Okay, so there is a reason also for that. Once we get to know the other topics as well, it will become clear to you why we are using the first notation. Okay, but you can use anything, it is your choice, but in these lectures we are going to use the first notation. Now from the matrix equation Vp is equal to AVS, if we know the symmetrical components, then we can get the original phasors, right? But sometimes and most times it is also required to get the symmetrical components from the original phasors. So we want to express Vs in terms of some equation, right? So what you will do here, you will simply pre-multiply by A inverse, right? So A inverse Vp is equal to A inverse A into Vs. So what will be the equation? The symmetrical components is going to be A inverse of the original phasors. So this is the expression. So now we need to find what is A inverse. Okay, so you can try it out later. I will write the final answer. A inverse you can get by adjoint A by determinant of A, right? So this you are going to get 1 by 3 1 1 1 1 alpha alpha square 1 alpha square and alpha. Okay, where you also mention what is A here, because we have seen two different A's, right? So we will write down here where A is 1 1 1 1 alpha square alpha 1 alpha alpha square. Okay, for the other A also we will write what is A inverse. Okay, so this is equal to 1 by 3 1 alpha alpha square 1 alpha square alpha 1 1 1, where A is equal to 1 1 1 alpha square alpha 1 alpha alpha square and 1. Now here you can see when you are taking the first notation, A is this matrix, right? If you compare A and A inverse, what you are seeing, the first row is same, in the second row 1 is the same, position is same, alpha and alpha square are being interchanged, right? Even in the third row 1 is the same and alpha square and alpha are being interchanged, and you have an additional 1 by 3 here. Okay, but in the second case, if you can see, the first row is not the same, right? It is changing. Similarly, the second row, it is also completely changing, right? So it is easier for you to remember the expression for A inverse if you are taking this notation. Okay, if you are taking this notation, it might get confusing. So I would suggest that you go with the first notation only, and that is why we are going ahead with this first notation only here in these lectures. Okay, now from this equation Vs is A inverse Vp, what you are going to get, the symmetrical components of a single phase, right? Va0, Va1 and Va2. But what if we want the symmetrical components of other phases as well? Okay, so from here, from the equation Vs is A inverse Vp, we get Va0, Va1 and Va2. Okay, so in order to obtain the symmetrical components of other phases, that is B and C, we can simply write Vb0 is equal to Va0. What is Vb1? This is going to be alpha square Va1, and Vb2 is alpha into Va2. Similarly, Vc0 is Va0, Vc1 is alpha Va1 and Vc2 is alpha square Va2. Okay, so this is how you can get the symmetrical components of all the three phases.